All right, guys, we'll jump into graphing logarithmic functions here. And first of all, we have exponentials and logarithmics back to back in this unit because they're inverses of each other. So exponentials and logs are inverses. Okay. So from the definition of inverses a while back, you know that inverses we can think of like flipping x and y. Okay, and we're going to talk about that. So our parent exponential, it had a horizontal asymptote at y equals 0, and it had a y-intercept of 0, 1. If these are inverses of each other, exponentials and logarithmics, then it would make sense that the parent logarithmic would have a vertical asymptote at x equals 0 and an x-intercept at 1, 0. Okay? Because they're inverses of each other. Okay? So let's start by doing a similar thing that we did with our parent exponential. Okay, we'll identify that x-intercept of 1, 0. Okay, so here's a log graph. F of x equals log. We call this base 2 of x. That's how this would be written. Okay, the 2 is called the base. All right, it just so happens if there is no base, okay, this is a base 10. Okay, if it just says log of x, that by default means a base 10. Okay, so things to think about there. All right, so all logarithmic graphs have the point 1, 0. Okay, all parent log graphs. And we have a vertical asymptote here at the y-axis. All right. Now the exponential is a shape that goes like this, and a logarithmic will be of a shape that goes like this. But we don't have to guess. We can plug in a table of values because we're still going to expect the same thing. We're still going to expect the shifted x-intercept. Here there's no shift because it's one of our parent functions. Okay. And then 2 points going away and 1 point going towards. Now here's the deal, guys. Again, if this is inverses, the way we found our other points, our table of values for exponentials, were by plugging in x and solving for y. Here, we're going to do the inverse of that. We'll be plugging in for y and we'll be solving for x. Okay. So if we kind of think of the general shape of an exponential graph, okay, we know that going away from the asymptote will be points above this point. This has a y-coordinate of 0, so let's plug in a y-coordinate of 1 and see what happens. Okay, we'll get 1 equals log base 2 of x. Now here's how we solve something like this, okay, and we'll get deeper into the solving of logarithmic equations down the road, but basically, all right, I like to use the terms slide, pop, and drop, okay? I know it kind of seems like some cool dance move that the kids are doing these days, but here's what we do. To get the x out from the log, all right, we're going to slide the base over to the other side of the equation. We're going to pop the 1 into an exponent, and then we get to drop the log. So this then becomes 2 to the first equals x, or x equals 2, which means we'll have a point of 2, 1 on our graph. Okay. Then let's try y equals 2. That would give us 2 equals log base 2 of x. We slide the base, we pop the number, we drop the log. That means 2 to the second would equal x, or x equals 4, which means we have the point 4, 2 on our graph. Let's do one in reverse here. All right, a y of -1. Okay. -1 equals log base 2 of x. We slide the base, we pop the number, we drop the log, we get 2 to the negative first equals x, or 1/2 equals x, meaning we have the point 1/2, -1 on our graph, and there is our logarithmic function. All right. So graphing our logarithmic functions, we're going to use our transformations. Okay, so we're going to shift the x-intercept. We're going to shift that 1, 0 point using our transformations. Okay, what would this point be affected by? It would be affected by a vertical and a horizontal shift. It would not be affected by a vertical stretch similar to the y-intercept because the y-coordinate is already 0. In a vertical stretch, we'd think about multiplying that y-coordinate by the vertical stretch, and anything times 0 is still 0. Okay? We will find the vertical asymptote. The vertical asymptote would only be affected by a horizontal shift. A vertical line would only be affected if it moves left and right. Okay? And then we're going to graph 2 more points going away from the asymptote. We're going to graph 1 point going towards by making a table of values. How do we do that? We're going to plug in y values. We're going to solve for x's. All right. So let's come down here and do this, this graph of our logarithmic function down here at the bottom. Then we'll talk about this ln and what that means. All right. So we have a shift of right 1, up 3, and a vertical stretch of 2. Okay, again, the vertical stretch really won't matter in terms of our transformations here, but it certainly will matter when we look to solve these equations. Okay. All right. So right 1 and up 3, that would affect that 1, 0 point. So our 1, 0, right 1, up 3 will now turn into 2, 3. Okay, from 1, 0, that would move to the point 2, 3. Our vertical asymptote horizontally shifted 1 to the right. So that's going to be at x equals 1. All right, now let's find 2 points going away from the asymptote. So let's plug in y equals 4 and 5. Okay, when y equals 4, we get 2 log base 4 of x minus 1 plus 3. All right. So let me give myself some space to solve this. We got to get the log by itself first, so we're going to subtract 3 from both sides. We're going to divide by 2. Now we're going to slide, pop, and drop the log. 4 to the 1/2 equals x minus 1. The square root of 4 is 2. 2 equals x minus 1. We're going to get x equals 3. Okay, so when y is 4, x is 3. We can do that more times, guys. Okay. If we really wanted to. Okay. I don't want to make this video take super long, but I guess we can. Let's plug in y equals 5. All right. So 5 equals 2 log 4. Base 4 of x minus 1 plus 3. We get the log by itself. Subtract 3, divide by 2. We get 1 equals log base 4 of x minus 1. We slide, pop, and drop the log. We get x equals 5. All right, we also would have a point going the other way. You guys can plug in y's and solve for x's. We've just done it 3 or 4 times. We would need one other point. I just don't want to go through that on the video. We'd probably want to plug in a y equals 2. I think we'd get 4 to the negative 1/2 power and go from there. All right, ln stands for the natural log, which is code word for log base e. That is the natural log. ln means natural log, means log base e. So my suggestion for you, we could rewrite natural log as log base e. This is a parent function because there are no transformations. So we have our x-intercept at 1, 0. We have our vertical asymptote at x equals 0. And then we would just go ahead and plug in values for y, solve for x. Okay, so if we want to go through one of those, if we wanted to plug in y equals 1, we'd have 1 equals log base e of x. Slide, pop, drop the log. X would equal e. That's approximately 2.7 or so. So we'd be able to put a graph there. We could find another point going this way, one going that way, and our graph would look like that. Okay. So we learned a few things. We learned that logarithmic and exponential functions are inverses of each other. Okay, here was kind of the start of that, where we talked about the properties of the parent exponential and the properties of the logarithmic exponential, being basically the switching of x's and y's. Okay, we talked about how to find extra points, being the switching of x's and y's. In logs, we want to plug in y's and solve for x's. We noted how we graph logarithmic functions, and we noted what the natural log was. That's it for today.